Satya.
Okay, thank you very much. Can you hear me okay? I actually wanted to ask the question, Einstein, where are you taking us? But I didn't know how to say that in Latin. So I just asked, Einstein, where are you going? So we can follow you. Moreover, this Quo Vadis is actually a brand name of slippers in India. And I was always fascinated by what the hell it meant. We didn't know what it was. We just thought it is another name. So anyway, very glad to be here and share some thoughts on what else needs to be done or what are the opportunities. So what we have heard over the past 5, 6 lectures is what has been observed. But I would like to start with what was not observed. I think that's pretty interesting. There is a long list of things that we can observe. And then I will go on to very briefly say what we might hope 2G and 2G plus detector networks to accomplish by 2025, and what other interesting problems remain in order to motivate third generation detectors. So that's the goal. So let's start with a list of different things that have not been observed. It's an unfinished story because this was a textbook kind of signal in which you hide all the complicated physics and just have a simple description, and that's what we observed. Namely, we did not observe a long adiabatic in spiral of tens of thousands of cycles, but instead only 10 cycles. Signals contain not just the quadrupole mode, the 2-2 mode, which is the dominant mode, but also higher order modes. And we didn't observe any of that. The black hole remnant that we observed seems to have a fairly boring spin value, only 67%. And that sounds like infinity to extremal spins, because extremal spins have a lot of very interesting physics, but we didn't observe that. And the component black holes, of course, we don't even know what the spins are because they're highly uncertain. We didn't observe spin-induced modulation. It might have been there, but we can't tell. And I'll explain to you what I mean by that. Because of the way the system seems to be oriented with respect to us, even if there was this very interesting frame dragging spin-induced modulation effects, but we didn't observe them. It may have had, but we don't know. Electromagnetic counterparts, there are no reasons to believe binary black holes should emit electromagnetic radiation. You heard from Samaya Nisanke yesterday, unless there is some environmental effects we don't expect. But nevertheless, we did seem to have some reports about that, and I will just have a slide to describe that situation. And finally, but that's what I'm going to start off with, we didn't observe late-time quasi-normal modes. Let's actually pick that particular topic and start off. Late time is in parentheses is there because we really don't know when is late time. With respect to this particular signal, is it 1 millisecond, 5 milliseconds, or 10 milliseconds? That itself occupied the collaboration for a good part of several months of discussion. That was not the only thing we were discussing, but we were engaged, and it's still not settled. And that's because we have an extremely dynamical remnant when it forms, and it cannot be described by linear perturbation theory to begin with when the two black holes merge. And it requires nonlinear description, but the peak of the amplitude is already past, and we think that we have a fairly a system that's going to settle down soon into a quiescent mode.
User in your channel timed out.
Description of that. Is there a question, something? So one of the things that we could do is what popularly we say as test of the no-hair theorem. It's not as if the theorem is tested. The theorem is true. What we mean by that is that object that we observe, does it obey the no-hair theorem? That's what we mean by it. So you have this pair of black holes coming together and merging, and initially it is highly deformed. And these deformed black holes, if the deformation is small, are known to emit a superposition that contains infinitely large number of modes called quasi-normal modes. They are complex frequencies in the sense that the modes decay rapidly, and measuring two or more modes, because if you just measure one mode, that's a complex frequency, it's a frequency and a damping time, you can infer what's the mass and spin magnitude of the black hole. And if you measure more than one mode, there's a hope that you can actually test whether or not it's a black hole, because all mode frequencies depend only on those two parameters, the mass and spin. So that's what we mean by testing if this object is really a black hole or not. If modes depend on other parameters, consistency between different mode frequencies would fail if you assume that it is a black hole. And thereby, we can provide a smoking gun evidence for a black hole. So that's the goal. But what did we observe? So you have seen this slide several times over now. And what you see is a few cycles. And after that, after reaching a crescendo, it simply abruptly terminates. If you then ask, how is the frequency of this signal changing? We looked at the best fit model, which is in white. And then on top of that, there is some uncertainty as to what the signal might be. That's in red. And you then go and calculate what is the temporal frequency as a function of time. And if you plot that, it's adiabatically increasing, and then finally, it is a very rapid increase. And then there's a constant frequency which signifies or indicates that you have a black hole or an object settling into a quiescent mode. There's nothing more happening after that, no dynamics. So this is the point at which the peak frequency is reached, about 0. And if you then ask, but you know, frequency is still raising. It's not settled down after reaching that amplitude. And if you ask, what is the frequency at which this is settling down, or rather, when is it happening? It is about 7 milliseconds after, or in terms of number of cycles, it's about a couple of cycles after reaching the peak amplitude. So let's go back to the signal that we observe and ask, what is there a couple of seconds? 7 milliseconds, or a couple of cycles. Well, this is consistent with background noise as far as the eye can tell. But it is not just the eye, because we can detect things which are buried inside noise, provided there are enough number of cycles. But the problem is, if this is really exponentially damped signal, and there aren't many useful cycles after that, there is nothing much to be gained. And our estimate is that we probably have a signal-to-noise ratio of a few. Depends on where you put this cutoff. You can get 2, you can get 5, you can get 7. Really depends on playing with this. And that has to be compared with the total signal-to-noise ratio of 25. There is nothing much significant that we can observe and claim about quasi-normal modes. As I said, why are quasi-normal mode important? quasi-normal modes important? They are important because they are the true test whether the final remnant was a black hole or not. Even though we do claim that this is a black hole, that really comes from agreement of our numerical relativity waveforms with the observed signal, which is done for binary black holes. So that waveform consistency is the reason why we think it's a binary black hole and the final remnant is a black hole by just inference. In order to provide a full convincing test to a skeptic, then we need to really test this no-hair theorem. That may not be. That may not be. In fact, I thought I will include a slide or two as to what kind of signal-to-noise ratios are required. And it turns out if you have a signal-to-noise ratio of 500, okay, roughly, then it's not inconceivable to see 3-4 cycles. At the moment, it's completely submerged, but even if you have 10 times more signal-to-noise ratio, you immediately start seeing them. And it's not inconceivable we'll see that sometime in the future. Especially with space-based detectors, they will last for several minutes, just the quasi-normal mode ringing. And we should be able to count the cycles above noise and really infer things. Something that needs to be looked at in the sense that we need to characterize quasi-normal modes in a way that is independent of the masses. We began doing it with John Veach and also Sarah Gozan, where we introduce parameters that are independent of the mass and spin of the system, and then it should be possible to combine. And a recent paper by Maydam et al., which again we co-authored, we did combine signals, and I think in advanced LIGO, if you have tens of events, then it should be possible to test this. John. John, you had a point? Oh, Maydam paper, yeah, okay. Yeah, absolutely. In fact, day before yesterday, I don't know if you were there, we had a long discussion. We are throwing away very useful part of the signal when doing the analysis. There is theoretical work required here, just numerical simulation saying, hey, that's the signal. After the two black holes have merged is not enough. We need analytical insights into how do black holes that are highly perturbed behave. And that's something very urgent and needs to be done quickly and has potentially high impact in our understanding of how black holes settle down to quiescent state. Yeah. Yeah. The quasi-normal mode, the way the damping time, that is simply inversely proportional to the mass, whereas, no, is that correct? It's proportional to the mass, whereas the frequency is inversely proportional to the mass, but different dependencies. And by looking at the frequency and how quickly it is dying down, you can uniquely tell what's the mass and spin of the black hole. Stack, I didn't. Oh, the stack, yeah. What we do is to introduce extra parameters. And we say it's not omega, but omega plus delta omega. If delta omega is 0, then that's consistent with general relativity. And for each mode, we can introduce a delta omega 22, 33, 32, 21, whatever we want. And that's how we stack up things. Yeah.
Given a finite number of quasi-normal modes, you can always check whether this is consistent with a black hole. But can you prove the uniqueness, like it has to be the black hole? Then only, like given a finite set of quasi-normal.
If you have more than 2 modes that you can observe, it's already, and if you have, exactly the same mass and spin for 2, it is a consistency again.
It's again
not
consistency.
It's
Strong
not a
consistency, but
I don't think you can prove anything by observation, right? You can only say, you can only disprove something. So it's only a matter of consistency, always. That's true. Yeah. At what pace? It's, it's after about 2-3 cycles of linear quasi-normal modes, you can consider it to be a single black hole. I mean, it's never in the sense that it is exponentially done, but after 2-3 cycles, there is nothing much in it. So Q factor is normally about 2 for non-spinning black holes. The highly spinning black holes, you can get 4, 6. Extremal, black holes is very large Q, but you never get that. Okay. So how does that quasi-normal mode look like, and what can we tell? Here is a graph from Gosson et al. Paper, where the black dashed line is just the 2-2 mode. That's the dominant mode. You can see that pretty much overwhelms all other modes. And here are 2-1 modes in red and 3-3 mode in cyan, and in blue it's the 4-4 mode. The 2-1 mode is, of course, half the frequency of the 2-2. The 3-3 is 1.5 times 2-2, and 4-4 is 2 times that. And if you superpose all of them, you actually get a pretty much distinct information. This dashed line is the spectrum corresponding to only the 2-2 mode. But if you then look at the total spectrum, you can see there are characteristic lines that come about. Even though they are weaker, they come about because there is interference between these different modes, and you get those features, and by measuring those features, we can learn about the object itself. So that's the goal. So we didn't do that, but we also did not observe higher order modes. What are these higher order modes? Not just the quasi-normal modes, but actually the entire in-spiral, mergering, and post-merger signal contains beyond quadrupole. If you have just the 2-2 here, that would correspond to a signal that we will observe corresponding to quadrupole deformation. But there are higher order terms, and it goes all the way, L goes from 2 to infinity, and M goes from minus L to plus L. So many, many modes that are present here, and we didn't really observe any of them. How do these modes look like? Sorry? Yeah. Yeah, absolutely, absolutely. I'll show you what we have seen and what we haven't seen, because I want to first give you a glimpse of what it would be if you include higher order modes. Let's take a signal from a 3 and 10 solar mass system. It's not quite what we have observed, but something like 3 and 10 solar mass system. But I'm looking directly into the orbit. That means the line of sight is along the orbit. Then in white, I plot what is called the restricted waveform, which contains only the 2-2 mode. And in cyan, I am plotting the full waveform, which includes all the modes that are relevant. And you see that the two are sitting on top of each other. And in order to tell whether there is any difference, I have to take the difference between those two, and the pink tells you that difference. Well, there is some difference, but not a lot. But as you make the system more asymmetric, okay, then the signal becomes weaker. But you will see that as I change the orientation of the system, the difference between the 2-2 mode and the full actually becomes larger and larger. And there is a lot of information that is contained in these higher order modes, and we can use those modes to learn about the dynamics of binary black holes, but also they break certain degeneracies that exist in parameter measurement. And in particular, they actually help better localization of source when the system is asymmetric. Yeah. They do contribute, yes, absolutely. It's a post-Newtonian expansion for F dot, and there are contributions both from the 2-2 mode and from other modes, and it can change. It doesn't have to always, accelerate. It can actually decelerate because of the presence of higher modes as well. Yeah, so that's possible too, absolutely. So we didn't observe them. We have no clue whether this is present or not. And I will show some other slides later on to say that. We didn't observe extremal spins. Yeah. No, unfortunately, we don't have, well, gravitational wave observations are the only ones that can actually tell you something about orientation of the system so far away. The problem is when the system is face on, we can't really tell the orientation up to a certain angle, actually. Even up to 30 degrees, it is very degenerate with the distance measurement. I think if it is beyond about 30 degrees, we can begin to tell. And that's also present in this description here. When it is 45 degrees, you can see there is substantial difference between the two different models that I used to extract the signal. Obviously, if I used only the quadrupole mode, I would be making a pretty, biased conclusion about what the system is, how it is behaving. And in fact, this is what we had to do. I mean, these are the kind of things that took us time. We had to use, this is still ongoing study where we are trying to use higher order modes. We did some of that, John, in the study for the event. Did we use higher order modes at all? Yeah. This is unpublished work. This is ongoing. Yeah. Okay. So you'll hear a little bit more later on about these things. Black holes can spin very fast. Actually, I'm running out of time already. And there are astronomical candidates, and astronomers for long have claimed that they're observing extremal black holes. So one of the hopes of gravitational wave observations is to resolve that question whether black holes really spin extremally wherever you look at them. The one that we saw is actually pretty boring. It's only about 70%. Even though I say 70% sounds like a lot, but the spin effects are really not at all important when it is even 70%. It begins to become important when it is 90%, but not even, maybe 99%. And I'll show you what is really the big deal if we have large spins. We know something called spin-induced precession, which is very special to general relativity. It's not present in Newtonian dynamics. And what is it? If you have an orbit of a binary, it has an angular momentum. And in addition, if you also have spin of, or let's say one of the black holes, then the total angular momentum of the system, J, is misaligned with the orbital angular momentum. And what general relativity predicts is that orbital angular momentum must precess around the total angular momentum J. So the orbit actually changes in the course of this. And if you look at then the orbit, it's not a planar orbit anymore, it's a precessing orbit. So if you are observing this system then, you are not observing it with one particular orientation at all. As time goes on, it keeps changing. What is important is to have unequal mass, and also unequal mass will make it precess a lot more than if you have equal mass. The system that we observed are more or less equal masses. We wouldn't say that's highly asymmetric system at all. And so the a precessing binary black hole would be consistent with general relativity because precision is not going to be a lot in this system. But what can we say about the waveforms? If you have a non-precessing system, and if you look at it face on, then the waveform is going to look something like this. But even if it is precessing, if you look at it face on, then it looks almost the same. Nothing much to gain. However, if you have an edge-on system, deliberately chosen to be edge-on so that you can amplify, we can actually detect precision, even smaller precision, but this is just for illustration purpose. You see, the non-precessing system really doesn't change at all. But the precessing system has a lot of modulation. And this is not what we observe. The system could actually be this, but we have observed it edge-on. It's perfectly possible. But the bottom line is we didn't observe those precision. And there's a lot of general relativistic dynamics. It will be fantastic to observe them someday. Electromagnetic counterparts. Well, binary black holes are really not expected to emit any electromagnetic signatures, unless, of course, it's buried in some environment, gas-rich environment, or plasma, or something like that. What has been intriguing, but I call it opportunistic, is that the Fermi Gamma Ray Observatory seems to have found a trigger just half a second after the merger of this black hole, but it is a sub-threshold event. It's not an event that they would have reported immediately. Of course, they do take into account what is a chance of such a thing happening, but I don't know whether they're folded in things like trials factor, that is, which one statistically gets bogged down. I don't know how much of that really went on. So we will have an opportunity to question them, I hope, in an upcoming gravitational wave and astronomy workshop. Observing, of course, EM afterglows could be a huge paradigm shift for astrophysicists. You don't expect to observe, but what if there is one? And Avi Loeb actually put up a preprint immediately after the announcement of Fermi, and some very exotic kind of scenario for what this electromagnetic counterpart might actually be from. Moving on, exploring black holes using gravitational waves is a huge opportunity. There are many, the whole parameter space is massive. Let's actually start with this slide that shows you mass in this x-axis over 12 orders of magnitude, and frequency, likewise, 12 orders of magnitude, because gravitational wave frequencies are simply inversely proportional to the mass of the system. We don't observe all of them in a single detector, but we do have opportunities to observe from ground, from space, from pulsar timing arrays. They span different frequencies. These are audio frequencies. These are millihertz frequencies. And these are nanohertz. Down here, gravitational wave periods are of the order of lifetime of a physicist. 30 years, 100 years, something like that. Over here, it's of order hours, human timescale, where you can observe many, many cycles during the course of your observation. And here, of course, it's very interesting. So what can we observe here? If you look at the last stable orbit frequency, it's simply 1 upon m. Most of them are 1 upon m. Okay. But some power law of m. And here, this is the quasi-normal mode fundamental frequency. It's the 2-2 mode. But that's not the only frequency that we hope to observe. We also have higher order modes, as I mentioned. And, that's the last stable orbit frequency. And the frequency at the peak amplitude is this. I'm sorry. This is the frequency at the peak amplitude. And we observe systems to the left of these lines. Therefore, the systems that we observe are sub 10,000 solar mass black holes for ground, between 10,000 and about 10 to the 8 solar mass black holes from space, and really very giant supermassive black holes for PTA. That's the range of observation for PTA. Now, in addition to this frequency at peak amplitude, as I said, the system continues to evolve and that's the 2-2 frequency mode. But it's not the only mode that we observe. We also observe 3-3 and also 4-4. And beyond that, numerical relativity seems to suggest we don't have much power in higher order modes. Therefore, if we see any radiation in this region for a particular mass, let's take a 100 solar mass black hole, if we observe something in this region of hundreds of hertz, several hundreds of hertz, that would indicate that it's not a black hole, it's something else. Because we don't expect any radiation. You're inside a black hole. Plotted also on top of this is a line that represents a point from which, if a system starts, it will take just 1 minute to merge. You can see if you start with something like 10 hertz, which is that point over there, then the system lasts for about a few minutes for tens of solar mass black holes. Not much longer. But if you look at, so that's for a binary neutron star, that would last for about a minute starting at that particular frequency. But if you draw the line for 1 day to merge, starting from that point, 1 day to merge, you see that most of the systems that we observe in ground will last for less than a day. Anything to the right of that dotted line will last for less than a day. And only when you have light binary neutron stars will it last for at most a week in our detector. Which means that the systems that ground-based detectors observe are essentially coalescing binaries. So that's why we call them coalescing binary search. They don't really stay put in the same orbit. Also, they can last for several years. You know, this is 3 years to merge. And that's the kind of systems that LISA, the space-based detector, will observe. But the systems that PULSAR timing array observes, that's several years. But systems that PULSAR timing array will not even change in frequency. They stay put in the same frequency. You can't even measure the change in frequency over a 30-year time scale. So that's the landscape. But what does it tell for us about the maximum distance to the type of systems that we have observed? Namely, heavy mass black holes. That's the maximum distance at which we can observe GW 150914 in various different detectors. This is advanced LIGO design sensitivity. This is improvement over advanced LIGO design sensitivity. And that's a 3rd generation detector. What you see here, redshifts beyond 1 at advanced LIGO for this system. That's the maximum distance. And this is several, redshifts of several. And in Einstein telescopes, several 10 C1. But that's not normally what is important. What is important is the average distance at which GW 150914 will be observable. And that might be more like redshifts of about 10 for ETB, an Einstein telescope, a 3G detector. Like blue is redshift of 2. And here, it's about redshift of a fraction of a redshift, something like 0.5. So what can we do with binaries not only of the type GW 150914, but several other systems that we potentially have the opportunity to observe in the next 10 years or so? These are intrinsic masses, and they can be seen at greater distances, and therefore they will appear to us heavier, and we have to shift them. Therefore, the observed mass is much larger than the intrinsic mass, and therefore the peak appears. What is happening is the lighter systems at greater redshifts appear to be so massive that they move out of band, and therefore the peak appears at an heavier mass. Why it comes down is because, as you keep increasing the mass, of course, the amplitude of gravitational waves is increasing. But the frequency is also decreasing. And the gravitational wave detectors have a wall at a certain frequency. In the case of the detector now, it's about 30 hertz. Advanced LIGO aims to go up to 10 hertz. For Einstein telescope, it's more like 1 hertz. And these are the things that really determine where it begins to fall off. That's the reason. So I have just put some bullets to understand what might be possible by 2025. We might have measured the rate and confirm the existence of binary black holes, neutron star black holes, and maybe even confirm GRB progenitors, but probably not much else. By that, what I mean is we wouldn't have really settled down on various astrophysical models for binary populations. How do they form and evolve? Do they form in clusters? Do they form in isolated binaries? And maybe a mixture of those, and what are the properties depending on where they form, spin tilts and mass ratios, precessions, and so on. In order to do this, you need a census of what's out there. And that's only possible when you have thousands of these systems, and that won't be possible with just advanced LIGO detectors. We will begin to detect 1 event per day on average, but that still means that if you have a duty cycle that allows you for something like 50% of the time it's up, you still have only several hundreds. And I think our first guess, in order to do proper astrophysical modeling, you need several thousands, and that would not be possible in the near future, although people start doing astrophysics even with 1 event. Okay. It's mostly from the, starting from this Belchinski's long list of models, and we started asking the questions. If I want to really distinguish between the different models, I create a catalog. It's unpublished work, I have told you about it. Unpublished catalog, unpublished work, but you create catalogs. And then you see that with several hundreds of sources, you still have some degeneracies that you cannot completely break. But maybe those degeneracies are hard to break. And when you have large numbers, you can still, you can hope to break. I'll show you one slide later on, not in this talk, but say it again. Yeah. This particular combination of masses. I thought at least one of his models did. Are you saying all of his models are? Oh, they don't. Oh, what you mean is many of his models don't predict these heavy mass black holes. Yeah. Okay. No, I agree. I mean, this heavy black holes that we have observed have knocked down some of the models. Yeah, I agree. But the problem is distinguishing between the cluster that formed and isolated, and this seems to be still completely consistent with either of those. That's what I mean. But they may be both populations, and the question is, which ones belong to those, and what is driving the dynamics. That kind of detailed astrophysical models will probably require several hundreds or several thousands, and that's the point I'm trying to. It's unlikely that advanced LIGO or its improvement would detect supernova or magnetars. The reason for this is revised estimates of supernova amplitudes in gravitational wave window. It may be only about 10 to the minus 8 of a solar mass when a supernova goes. And that would make it very difficult to observe them unless they are in our own galaxy. And in our own galaxy, the rates could be 1 per 30 years to 1 per 100 years. And so the chance of observing supernovae with advanced detectors, which have a range, if it is 10 to the minus 8 or 10 to the minus 7, only within our own galaxy is very dim. We will have to wait to see these systems up to 2 to 5 megaparsec, where the numbers then are such that you might hope to observe 1 per 5 years or something like that. So even there, but even observing one supernovae or one magnetar still be extremely interesting because it required only one 1913 plus 16 to get a Nobel Prize and to understand the physics of compact systems. Neutron star ellipticities could be really low. That's what is being hinted. If you look at upper limits set by LIGO observations so far, it's 10 to the minus 7 for the fastest spinning neutron stars, which means that in order to really observe some of the potential sources, you need to go to third generation detectors. But of course, we'll be happily surprised if that is not the case. But the current estimates seem to suggest we need to go an order of magnitude better sensitivity. In terms of cosmology, advanced LIGO and VIRGO and advanced LIGO Plus would observe black holes when the universe was about 3 to 8 billion years old. That's the estimate that comes from how far we can see the system. And by this time, the universe has assembled its galaxies. It is not in its early growth, whereas the third generation detectors will observe when the universe was only about 650 million years old. That means that the universe was in its infancy, assembling the first black holes from the perturbations that were created in the early universe, and it would be fantastic to follow the growth of black holes starting from that. So what can we say about fundamental physics? That's the final topic. After that, I'll begin to summarize. Fundamental physics by 2025, equation of state of neutron stars would require 20 to 30 events, or few within 50 megaparsec. These would be possible in advanced LIGO and advanced LIGO Plus era. So what would remain? Well, this would probably fix neutron star radii within maybe 2 kilometers or a few kilometers, 3 to 5. But to get down to 500 meters, which is what nuclear physicists would like us to achieve, then we would need to go beyond that. More number of events, but also brighter, closer events. Closer, relatively speaking, for Einstein telescope might be still 100 megaparsec or 200 megaparsec binary neutron star event. It would be fantastic to fix the neutron star radius to within 500 meters. I really worry about mentioning anything about cosmography, dark energy, equation of state, or anything else, but we have the capability. But to do dark energy equation of state would require thousands of binary neutron star events and will only be possible with third generation. However, people are gearing up to use the unexpected large rate of binary black holes to do cosmography without obtaining any redshift information. And over the next 3 to 5 years, we might see theoretical advances where without EM counterparts, to do cosmography by identifying galaxies and doing statistical studies is looking promising, but nothing concrete as yet, except some preliminary investigations. Testing gravity would also require hundreds or even thousands of events. And again, the precision test will only come in third generation era. So with all that, what can we set to be a strategy for third generation detectors? I bring it up as a discussion point. I think it's best to focus our attention on a few very strong messages, something that this discussion meeting on Monday also endorsed. Instead of a long laundry list of things, as Rana would like to say, we should probably have only a few strong cases, strong messages. These are the niche points, things that only gravitational wave detectors can do are the ones that we should be thinking about. Identify 3 of the most important problems. That's what I tried to do, namely, a possible scenario for third generation detectors going forward might be extremes of physics, black holes through cosmic history, and explosive phenomena. Just one brief slide on each of these. Understanding extremes of physics, by that I mean, what is the most compact object in nature? And in fact, while doing the Einstein telescope conceptual design study, one of the things that we asked was, is there a state of matter beyond neutron star and black hole? There seems to be a gap between neutron star observations and black hole observations. That could be entirely due to stellar processes. But the question still remains, between something like 2 or 3 solar masses up to 5 solar masses, are there objects that could exist? That would be an interesting question to answer. What is the equation of state of neutron star cores? We have heard about this quite a lot in this meeting. Black holes through cosmic history. What is the nature of black holes? How did they form initially? And how did they evolve and grow to become these supermassive black holes of 10 to the 6 to 10 to the 9 or even 10 to the 10 masses? And finally, probing the transient universe. What are the progenitors of gamma ray bursts, and why is there such a variety of them? Almost every gamma ray burst seems to be different. What is the reason for it? What causes core bounce in supernovae? There's very little theoretical understanding of how supernovae really operate. We can gravitationally collapse them numerically, but we cannot bounce once they collapse. Why does it happen? So there are examples of exotic signs. We have seen them already in this conference, measuring neutron star equation of state and concluding what is the component, what is the composition of neutron star cores, whether it is free quarks or whether it is confined quarks in the form of neutrons, would be interesting. And I mentioned about neutron star binaries being used as standard candles, but maybe they can also be used as standard spectra, and I call it neutron star binary spectroscopy. The basic idea is that in-spiral signal is followed by a merger waveform. This is the in-spiral part, this is the merger, and this is the post-merger. And that could last for several milliseconds, several tens of milliseconds to even seconds, is what the theory seems to predict. So the signal really depends on the neutron star equation of state. The merger signal depends on neutron star equation of state. And for most equations of state, heavier neutron stars are smaller, and so larger post-merger oscillations, because frequency depends on 1 upon the psi. So, but here is the tension. If you look at cosmological expansion, that causes the frequency to redshift. But the observed mass of the binary is larger because the frequency is moved to lower frequencies. They appear to be heavier systems. If the system is heavier, they're actually smaller, and therefore the frequencies must be greater. So there is a tension between these two, and it happens only for binary neutron stars, not for binary black holes, because heavier black holes are bigger as opposed to neutron stars, where heavier neutron stars are smaller. And this tension really is what can be exploited to measure redshift to binary neutron star systems. We have just begun this exploration, and a lot more needs to be done. But it's an example of the kind of things that we should be able to do. So there it is again, the 3G signs, extremes of physics, black holes through cosmic history, and explosive phenomena. But there are many other opportunities to observe them. I just put a few here, the timescales for telescopes and mission surveys, going beyond gravitational wave observations and observing them in coincidence with other electromagnetic telescopes, many different opportunities. Since I'm just 2 minutes, let me just show all of them here, and thank you for your attention.
Can you go to slide 35? I think there you were summarizing what would be possible by advanced LIGO-like detectors. One thing I would like to maybe flesh out is that perhaps we can establish if intermediate black holes exist, mass black holes exist or not.
That's very much possible.
Right.
Only reason for not mentioning it is these intermediate mass black holes, if they form, they probably form very early on. And they really grow. What I mean by that is this hierarchical growth of galactic centers seem to posit that you need to form these black holes at redshifts of something like 10. Even third generation detectors cannot observe intermediate mass black holes at redshift of 10. Very ironically, we can observe hundreds of mass solar mass black holes up to redshifts of 10, but not thousands of solar mass. So maybe possible, maybe not. I didn't include that because it's not very clear about their existence and rate of merger.
Another point was that, yeah, talking about GRB progenitors, yeah, those may get confirmed. But do you hold out hope for doing some more? For example, establishing what the host galaxies might be like. Of course, that requires at least a few coincidences, electromagnetic and gravitational waves. LSST will be in operation, but we still need higher
I think
rates.
If we had made our first detection in binary neutron stars, we could have been more adventurous in speculating. At the moment, we really don't know what's the rate of binary neutron stars. And one thing that worries me is what Belchinski used to tell, that if binary black holes are in abundance, your luck with binary neutron stars is going to be very bad. That's what he said. I mean, he may not be correct. But going back to gamma ray burst connection then, if gamma ray bursts occur 10 per gigaparsec cube per year, then it's possible to have 40 binary neutron stars in design sensitivity only if the opening angle is 5 degrees. And so all boils down to what's the jet opening angle in gamma ray bursts. If it is isotropic, we'll still observe 1 per few years. So advanced LIGO is definitely going to observe binary neutron stars, in my view. But what that number will then determine whether or not we will resolve that question. At the moment, it looks as though we will have to wait to resolve, I mean, especially coincident observation, we'll have to wait for some time. It won't happen sometimes.
You mentioned about precession due to frame dragging. Now, of course, our focus is always on the horizon, but there's also the ergosphere.
Yeah.
And what is known is that the precession frequency, the lens steering precession frequency, diverges on the ergosphere. So if you could have a handle on strong gravity precession,
right,
it would be a very large effect.
So you're saying if you really observe extremely extremely spinning objects and also high precision.
Yeah, well, the ergosphere is the largest.
Why I'm saying extreme black holes is the precisional effects are larger.
Largest for the
That's
extreme.
not a sufficient condition. They also have to be off the axis.
Off the axis, yes.
Off axis and extremal spins will, okay, that's
the precession frequency actually diverges on the ergosphere. That's even for non-extremal black holes.
Good point. John?
Can I? Me?
Go ahead.
So about the intermediate mass black holes, I just want to say that what you say is right about the hierarchical assembly, but people have also argued that the ultra luminous X-ray sources are intermediate mass black holes which are accreting, and people have speculated that globular clusters may have intermediate mass black holes. So those would presumably be accessible.
Yeah,
if it's true.
I know, but our expectation was damped after one of those candidates was shown to be neutron star. Do you know about this, Vijay? One of the intermediate mass black hole candidates was explained very recently in a Nature article. I know Sri Kulkarni is one of the authors, but there are other people too. They showed that the origin could be actually a neutron star. And that completely blew me out. That here are ultraluminous X-ray sources. The most plausible candidates were about 300 solar mass objects. But here comes an observation that tells unlikely to be a black hole. It's a neutron star.
Yeah, but I think that's still contentious, is my impression. My impression is that it's still contentious. I also wanted to ask, are there separate estimates for what could be the number of binary black holes, neutron stars, etc., in the Milky Way and in the Magellanic Clouds, sort of thing, because they are in
binaries themselves?
Binaries, which could then inform estimates for gravitational wave detection?
Uh,
Because they would be really close by, right? So
yeah, I'm trying to see if I can quickly, I don't know the answer on top of my head. Never worried about it because when we did it for Lisa, it was not important to create a confusion background. That much I know. We know that white dwarf binaries are large in number and relevant frequency band to cause a confusion background, and they are about 100 million white dwarf binaries. The neutron star binaries, if they were present at that number, would have been too large. Maybe they are much smaller, maybe a factor of 100, maybe on one of them. That's the rate. Yeah, I would say it's a lot less than 100 million binary neutron stars or black holes in the galaxy. In that relevant frequency band, actually you're asking a very broad question. Actually, I don't know the answer at all. I should not be saying what I said. Because the white dwarf binaries I said is in the frequency band between something like 10 microhertz to about 10 microhertz to 10 millihertz, 100 million. No, so yeah, I take back my word.